So today we're going to talk about taking the atom or the atomic model a little further than we did in the last unit with the Bohr model. So the Bohr model was an advancement over the Rutherford model of the atom because it had energy levels. And so if you look at the these areas around the nucleus where the electrons were allowed to exist, Niels Bohr was the first person to come up with that idea, and it was the right idea, but then there's more to it. So one of the problems is when we start looking at bigger elements, bigger atoms, like for example neon, which is going to be a lot bigger than hydrogen, we have all these distinctive little bands of color. We have, multiple different shades of red and yellow and orange that are being given off by neon as it gets heated. And simply having a couple of different transitions between the energy levels for these electrons does not account for where we can get all of these different energies of light. So there had to be a better explanation or a further explanation. So about 15 years after Niels Bohr proposed the model of the atom that had the energy levels, a guy named Werner Heisenberg, among a few other people, came up with this idea that instead of thinking about electrons as being little particles that are orbiting around the nucleus, like planets going around the sun, which is kind of what I'm drawing here. So if I have a little electron, it doesn't just kind of go around the nucleus the way that the Earth goes around the sun. In fact, you can't really even think of it as a particle the same way that you think about, the planets being these big giant particles going around another particle. It's a little bit more complicated than that. It's kind of more like if you could imagine being in a dark room and you let out a firefly, the lightning bug. You'd be able to see that lightning bug light up, but because the room is dark, when it's not lit, you won't see the lightning bug. So it'll just sort of pop up kind of, here and there and everywhere in the room. Let me use a different color here so you can see it better. So what you'll end up with is these little points of light showing up. And if you took a picture every time that lightning bug lit up and you laid those pictures on top of each other, you would end up with an image that's basically just, and I'll draw this picture off to the left here. So if the red is my nucleus and the blue is my little lightning bug points or electrons really, they're going to light up here and there, and then maybe the next time here, and then maybe one way over there. It's going to just sort of randomly pop up here and there throughout the space. And that's the way that Heisenberg told us to think about electrons. Basically, he said, instead of thinking of them as being planets going around the sun, think of them as just these little points, these little dots that show up and then disappear in random places. We don't know anything about their path, really, how they get from point A to point B, which is why he said the more we know about the position of an electron, the less we know about its momentum, meaning that really small, really fast objects, we can't really know both where it is at any point in time as well as its velocity, how fast it's going. So what Heisenberg gives us is this graph where we have probability along the y-axis, and I don't know if you can see it, but there's a little p right there. That means probability, and then we have radius along the x-axis. So what he's saying here is as we travel away from the nucleus, when we get to a certain point away from the nucleus, we have a really high probability of finding an electron. So basically what that means is energy levels exist, but they're not really like the very strict the very, very strict little lines or radii that we would have imagined with Bohr's model of the atom. But instead, all we can really tell is where are we most likely to find the electron at any given point in time. And so that would be like the peak on this little probability graph. So where are we most likely to find the electron in this hydrogen atom, let's say? Apparently, the dotted line is at 0.0529 nanometers, so that's where it's most likely to be found. But you'll notice the probability of finding that electron never really goes all the way to 0. So that means the electron, is most likely to be found within that radius. Let's say that radius is about right there on my atom on the left. But it's possible that electron could pop up way out here or even further away. But most of the time, 90% of the time, it's found within this sort of, this distance away from the nucleus that's shown by the graph. So these two pictures basically are illustrations of the same thing. These are probability scatters or probability graphs of finding an electron. So these are just both two pictures of the same thing. You can imagine it being a hydrogen atom because hydrogen is really simple. It has one electron. And if that electron, kind of like the firefly we were talking about earlier, if that electron just sort of pops up and from place to place over the course of some period of time, and you were able to snap a picture of it every time it popped up, you get pictures that look kind of like this. It'd be kind of fuzzy looking because the electrons are just or that electron, I should say, is just kind of popping up wherever it wants to within that space. And notice that you do have some electrons that are kind of way out here on the perimeter, and they would be sort of outside of that densest region. So we could say that this area right here is where we're like 90% certain to find the electrons, but there's nothing saying that the electrons can't exist further away. And the same thing over here. We have an area of highest probability of finding the electrons, but the electrons can still pop up out here away from the nucleus, even further. Okay, so atoms have electrons within these sort of cloudy areas where they're most likely to be found. And the two that you've looked at so far look pretty much like circles, or if you think about it in 3 dimensions, they look like spheres. And it turns out that energy levels most of them at least, can be divided further into what we call sublevels. Okay, so sublevel just basically refers to, okay, you take your energy level, kind of like Bohr had in his atom. So nucleus, energy level 1, energy level 2, energy level 3. But then within those energy levels, there are smaller divisions called sublevels. It's kind of like if you imagine a building, let's say we have like a 4-story building, and then within those floors, you have further divisions. You have rooms. And some floors might have more rooms than others. You could even have a floor that's just basically made up of one big room. And that's what we have with the atom. The first floor, the first energy level of the atom, so we're kind of talking about the very first ring here, only has one type of orbital or sublevel, or in other words, place where we're most likely to find the electrons. Because the first energy level is so small, this is all that there's room for. And that shape, or the shape of that sublevel or orbital, is a sphere. So what you see here with the picture, right in the middle of the page here, is an S-shaped orbital, or a spherical orbital. And you can see it kind of looks like a cloud, where it's most dense kind of in the middle, where you're most likely to find the electrons. Down here it says one orientation, because basically you could only have one sphere of a certain size. Otherwise, if I tried to fit another sphere on top of this one, then they would be occupying the same space. So we can only have one of these S-shaped orbitals at each energy level. And each orbital can hold 2 electrons. So I could have 2 electrons in this S orbital at the first energy level. I could have another 2 at the second energy level. It would just be a bigger sphere. And so on and so forth. But we can only have one of these per energy level. The next shape that you see here is a P shape. And essentially, it's just twice as complex as the S shaped. It looks like two spheres kind of side by side, where the nucleus would be right in the middle. So The nucleus would be right there where I have that red dot. And then basically, if you want to kind of imagine what p-shaped orbitals would look like all together, it's kind of hard to draw. But if you were to just take these three graphs and just set them on top of each other so that you had a p-shaped orbital that was kind of oriented like north-south, like this, and then another one that's kind of going east-west, like this, and then another one, I'll use a different color, but another one would be kind of coming out at you along the z-axis, like that, and also going back into the page a little bit. So we can have 3 of these per energy level. Now, be very careful that you don't have the wrong idea about how the electrons are moving. Remember, electrons are like fireflies. We don't know what their path is. All we can do is kind of see them pop in and out of existence, or just sort of, like pop up here and there. So just because it's, the orbital is shaped like 2 circles does not mean that the electrons are just going around and around in circles, like this. Okay, that's not what this is saying at all. It's not like one electron is over here doing this and one electron is over on this side doing the same thing. What we have instead is we just have electrons showing up sort of all over the place within these areas. And that's what makes up an orbital. And just like with the S-shaped orbital, each of these 3 orbitals can only hold 2 electrons, which is where we get this number 6 electrons per energy level, because if I have 3 times 2, that's of course going to give me 6. Then we have our D-shaped orbitals. So again, just even more complex than the P-shape, but they can still only hold 2 electrons. And I know that might be kind of counterintuitive. I've got this shape that has 4 parts to it. 1, 2, 3, 4. But even though it has 4 parts, it can still only hold 2 electrons. Because remember, these are not 4 separate things, really. This is one orbital that I have circled here. And each orbital, just like with S and just like with P, can hold 2 electrons max. All right? So remember, you want to think of these orbitals as just the places where we're most likely to find those 2 electrons. Now, since we can have 5 orbitals in D shapes per energy level, and you don't have to remember these little designations down here, the little 3dxy, 3dxz, all that stuff. All that's saying is there are 5 different ways that these things can be oriented or turned, and 5 different orbitals of the D shape can fit per energy level. So if we can have 5 of them, and each one can hold 2, that of course gives us 10 electrons per energy level that can be in this D-shaped orbital. And then the last one that we'll go over, really the last one that we have, is the F-shaped orbital, and it's twice as complex as the D. You don't have to draw all of those, by the way. If you just kind of draw maybe one of them, maybe whichever one's easiest, maybe that one, just to give you an idea of how it compares to D and P and S. That's good enough. But these things, despite, again, just like with D, despite being really complex, can only hold 2 electrons per orbital. And again, remember, these orbitals are not the paths of the electrons. The little parts don't represent actual electrons, but they just represent where the electrons are most likely to be found if it's in an F orbital. So 7 orientations per energy level, 14 electrons, because 7 times 2 is 14. Okay, now let's take a look at the whole atom. This little triangle is just like a graphic representation of the atom. And so if you imagine the Bohr model of the atom for just a second, we keep going back to that one, even though it's not complete. We have the first energy level, the second, the third, and the fourth. Okay, it's kind of ugly, but you get the idea. So this is energy level 1, 2, 3, and 4. Okay? Now, in energy level number 1, what this is telling you is we only have a single s orbital. Okay, so that's what this guy is down here. It's an s, that little pink color represents an s orbital, and there's only one in the first energy level, and it's in an s shape. So energy level number 1 can only have s. Okay? If we're in energy level number 2, we can also have s, but in addition to s, we can have p-shaped orbitals. And if you remember, p-shaped orbitals you can actually have 3 of per energy level. So anytime we have P, we can have 3 of them. All right. So in terms of the total number of kinds of sublevels at the second energy level, we have 2 different kinds. We have S and we have P. But since P we can actually have 3 of, so maybe I'll divide my box up like that into 3 parts, we really can have 1, 2, 3, 4 total orbitals or sublevels. And then once we get into energy level number 3, so it says principal level number 3, it basically just means the 3rd energy level out from the nucleus. Once again we have S, which we have 1 of at every energy level. Then we have our 3 P's, all right? So I'll go ahead and divide those up kind of like I did in the last energy level. And then I also have a bunch of D's. And if you remember from your notes here, we actually have, let's see here, 1, 2, 3, 4, 5 D's. So 1, 2, 3, 4, 5 D's in addition to our 1, 2, 3 P's and our 1 S. So while there are 3 different kinds of sublevels, we actually have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sublevels in the second energy level. And if you think about it, because each one can hold 2, and we have 9 of them, you may have heard this before, but the 3rd energy level can hold a total of 18 electrons, whereas the 1st energy level can only hold 2, and the 2nd can hold 8 total electrons, because of the fact that 2 times 1 at the 1st energy level is 2, 2 times 4 at the 2nd energy level is 8, and 2 times 9 is 18. And then finally, when we get into the 4th energy level, that's where we can have not only an S and 3 P's, so 1, 2, 3 P's, and 5 D's, but we can have 7 F's, which gives us 14 electrons. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, along with our 1, 2, 3, 4, 5 D's, our 3 P's, and our 1 S. So that gives us a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 orbitals. Each one can hold 2 electrons, so that is 32 electrons total that can be in the 4th energy level. Now, what does this all look like on paper? Well, sometimes you may have already seen this, but sometimes you'll see for an atom or an element an electron configuration given. And so, for example, for aluminum, we have 1s2, 2s2, 2p6, 3s2, 3p1. So we need to talk about what that means. First off, the big number out in front stands for the energy level. So in other words, the 1, the 2, the 2, the 3, and the 3. Those are giving you the energy levels for the electrons in the aluminum atom. And that's also called the principal quantum number. The letter, so like the S, the P, the S, the P, that stands for the sublevel shape, and we've already taken notes over sublevel shapes. And it's got a fancy name too, angular momentum quantum number. We don't really use that a whole lot, but you should know what that word means. Basically just means the shape, okay? Now, how do I get this electron configuration for aluminum? If I look at this chart, what this is telling me is how electrons are going to be placed into an atom, or how electrons would enter an atom. So this chart is a chart of energies of the different orbitals. So the lowest energy orbital that we have is the 1s. So this is the 1st energy level. It's the closest one to the nucleus. So this is the place that the electrons would, essentially you can think of it as where the electrons would most want to be, because they're negative and the nucleus is positive. So if I imagine an aluminum atom as being just this little positive nucleus Oops, better make that non-disappearing ink. So here's my little positive nucleus off here to the right. As I fill up the as I fill up the atom with electrons, let's assume it's starting with 0. The first 2 electrons are going to go into the 1s. So we have 1s2, meaning that my first 2 electrons would, if at all possible, if it's open, the first 2 electrons are going to go into the first energy level S-shaped orbital. And there are 2 of them, which is where, of course, we get the number 2. Now, if you look at the periodic table, you can see that aluminum is atomic number 13. So that means it has 13 protons, but it also means that if it's neutral, it has 13 electrons. And right now, we've only put in 2. So we have 11 more to go. So as we travel up in terms of energy, the next 2 electrons would actually go into the 2s. So there we get 2s2. So now we've used up 4. We've got 9 more to go. Then if I go up just slightly from 2s, you can see that we run into 2p. So 2p has just a little bit more energy than the 2s, and so that's going to be the next destination for my electrons. Now, if you notice from the drawing here, there are 3 little boxes, and each box represents 1 orbital. And if you remember in our notes, we drew pictures of p orbitals, and there were 3 p orbitals per energy level, and that's what these 3 boxes represent. 3 orbitals, and each orbital can hold 2 electrons. So that means I could have a total of 6 electrons in the 2p. So then, from the 2p, so now I've used up 2, 4, 10 of my 13 electrons. So I've got 4 more to go. So the next place in terms of energy would be 3s, okay? And again, 3, so third energy level, S-shaped orbital, and 2 can go in there because there's just 1 orbital in the S shape per energy level. And then, so now I'm up to 12, and here I'm just going to erase my little nucleus and get that out of the way. So now I'm up to 12. I need 1 more. So the next highest energy, or the next lowest energy, pardon me, would be the 3p. Now 3p has, if we look over here, 1, 2, 3 orbitals. At every energy level, the p can be, you can have 3p orbitals per energy level, whether it's 2p, 3p, 4p, 5p, 6p. Doesn't matter. So the p can always hold 6. Okay, 3 times 2 is 6. But in this case, we're up to 12 already. So again, 2 plus 2 plus 6 plus 2 is 12. And so I only have 1 more electron, and that's where it goes. It goes into the 3p. Now the chart that I just showed you is helpful for making these electron configurations, but there's another way to do it using the periodic table. And because you always have a periodic table available to you, it's a pretty good thing to learn how this works. Now, first of all, the periodic table can be thought of kind of like a stadium. And if you've ever been to a ball game, anywhere, you know that the stadiums are actually broken up into sections. Like if you go to Busch Stadium, you've got sections. You don't just have a seat number. You have a section, you have a row, and you have a seat. Like you might be sitting in section 205, row E, seat 14, or whatever. So this kind of helps you because you know what part of the stadium to go to, and then you can find your row, and then you can find your seat number. Well, the periodic table can be seen as a stadium in the same way. So we actually have 4 sections to the periodic table. And actually, for some reason, this periodic table is missing a couple of elements. We're missing hydrogen. And actually, for our purposes today, we're going to put helium up here next to hydrogen. But this first part over here on the left, we're going to refer to as the S block. And then over here on the far right, essentially from group 13 to 18 is going to be the P block. This middle section from group 3 to group 12 is going to be the D, And this bottom section, which we rarely use, but we should still know where it is, that's the F block. So all you're going to do is number our rows. 1, 2, 3, 4, 5, 6, 7. And when you look at the periodic table, we now have sections, or blocks we could call them, and we have rows. So when I'm doing the electron configuration for aluminum like we just did, can we do it without the chart that we just saw? Okay. So in other words, if I am not looking at this chart, can I still come up with this electron configuration? And the way we do it is we just simply go through each row, starting always up here at hydrogen, and we write down the row number, which would be 1 to start with, the block, which would be S, and the number of spots in that block. So as I'm trying to go to aluminum over here, number 13, I'm going to start off with 1s2 because I'm in the first row, the S block, and there are 2 spots that I'm going to have to walk through. Okay. Then there's nothing else really up here in this first row. It's just empty. There's no D, there's no P. So I have to come back down to the second row. And so now I'm at 2s2. So second row, S block, 2 spots. Okay. And then I'm going to continue. Now this time I do run into something else in the second row, and that something else would be called 2p. And because there are 1, 2, 3, 4, 5, 6 spots in the 2p, I'm going to say 2p, 6. And then I'm just going to keep going, and now I'm going to come down to the third row, and I'm going to run into 3s. And again, I'm going to go through 2 spots on my way to aluminum, so 3s2. And then I'm almost there. I've got nothing in the D block, but I'm going to keep going until I hit aluminum, and aluminum would be found at spot 3p1.